In this video, we'll do an application of a double integral, very common situation here where you have a very thin metal plate or some other material sitting in the xy plane, and it forms some region that I'm calling R. So I want you to think about some sort of little metal piece that's being fabricated, lying flat on the xy plane, and it's the shape of a circular sector. So the boundary here is circular. The radius of that circle is, I'm just calling some number A, which is some positive number. And then there is an angle that forms the sector slice of that circle that we're looking at, and I'm calling that angle phi. And phi is just some angle between 0 and 90 degrees, but fixed throughout our discussion at some constant value. Now, for whatever reason, the way this plate was manufactured, as I move through the plate into different points, apparently it has different densities, which means it's going to weigh more on different parts than it might at other parts of the plate. It might be a little bit thinner over here where it's lighter, and it might be a little bit thicker over here where it's darker, and therefore the density is changed and the mass or the weight of the object kind of varies as I move through the region. And that might be described by some function here. Here I have the function delta. It depends on a point xy. And apparently the density at a point xy is given linearly by 3 times x. And that's a density, so it's something like grams per unit of area squared. It's 3x grams per meter squared, or whatever units you happen to be looking at here. And what we'd like to do is find the mass of the plate. Notice as I vary the x-coordinate only, the density is increasing, and I've tried to capture that graphically. As you move across from left to right, it's getting denser. So let's think about how you would do this just briefly here, and then figure out how what this has to do with double integrals. Just imagine a small little bit of area of the plate, a little square of area, something very, very small. I'm calling that delta A, and delta A has a little bit of mass, which we're calling delta M, change in mass. And how do I calculate the mass? Well, I take the area of that little bit, and then I'm going to multiply it by the density of some representative point xy sitting in that little square there. And that's the sensible thing to do. I'm taking grams per square meter, that's density, and I'm going to multiply it by the change in area, which is in square meters, and I'm getting some grams amount, I'm getting some mass as a result. But I'm going to do this across that entire region, so I sum those up. I want to do this in a nice continuous way, and to do that I should do some sort of integral, right? I should take some limit here, let those little bits of area get smaller and smaller and smaller, and to get the mass I'm effectively doing a double integral. The function that I'm integrating is the density function, and I'm integrating that over area, and the notation here is really cluing you in that this is correct. Density, grams per square meter, dA kind of carrying the units of square meters, and when I sum up those little calculations, I'm going to get something in grams, I'm going to get a mass. So let's work on the specific problem that we have now. I need to find the double integral of my density function, which is 3x over this shaded region R. Very, very accessible if we do it in polar coordinates as opposed to rectangular coordinates. Would be much more challenging. So I want to do it in polar coordinates. So let's set it up that way, dr and d theta. The function that I want to integrate is 3 times x. You must convert that to polar coordinates. X in polar coordinates is given in terms of the cosine of my angle. So it's going to be r times the cosine of theta. That's our standard conversion from rectangular coordinates to polar coordinates. R times cosine is the x. Because I'm working in polar coordinates, I also get this factor of r, and that will be the expression that we integrate. We integrate 3r cosine of theta times r. We'll set up our limits of integration next. My angle theta, my variable theta, goes between the two extremes where theta is equal to 0 on this ray, and then when theta is equal to my chosen angle phi here, so my limits of integration will be 0 to phi. I then need to imagine a generic value of theta, which is some ray emanating from the pole, from the origin here, going along here. I'm immediately in my region, and then I exit when my radial value is equal to whatever the radius is set to, which in this case is called A. So we're going to integrate from 0 to A. This calculation here will tell me the mass, and let's go ahead and just do the calculation now. It is simply an iterated integral in terms of these two variables. So I'm going to clean it up first, simplify it. It's 3r squared cosine of theta that we are integrating. I'm going to integrate with respect to r first. That r squared is just the variable portion, and its antiderivative is going to be, for 3r squared, its antiderivative will be r cubed. Derivative of r cubed is 3r squared. The constant, the cosine of theta is all constant in this integral, so it's just going to be there as a multiple. I need to evaluate that between 0 and a, and I'm going to plug that in for r, so it'll be a cubed minus 0 cubed. I won't see that term, so a cubed cosine of theta. A is just a constant here, so I'm really just integrating cosine of theta and multiplying the result by a cubed. Sine of theta is the antiderivative, and I need to evaluate that between 0 and phi, so I plug that in for my angle theta. And it's going to be a cubed sine of phi, and sine of 0 will be 0, so I don't see that term, and that quantity is in grams. That's the mass of this thin little rectangular plate with that varying density.